Today I'm going to talk a lot about things you can do with Java that you can practically take back home and try yourself, and also some lessons about that we learned in the process of migrating Lambda's front end. My name is Ishai. I'm the general manager of Amazon Corretto, which is a distribution of Java from Amazon.
And I'm Niall Cannon. I'm an engineer on the AWS Lambda team.
So we'll start by introducing you to Amazon Corretto. How many people here have heard about Corretto before? Nice. A lot of you. Awesome. And how many of you have deployed Java 11? A little bit less. Anybody doing anything newer than Java 11? One. Okay. Good job. We're going to proceed to talk about Lambda's architecture, explore JDK 11 and how we deployed it and what we learned from it. These are some related breakouts. You might want to go if you have time. ACCP is a Corretto module, if you want to call it that way, that makes cryptography a lot faster. You can use it regardless if you use Corretto. And then some best practices for running Lambda functions using Java. And we're going to dive deeper in SVS 405 into Lambda's architecture, talk about CI/CD, and DOPE 404 is a really cool session about how Amazon does high availability deployment. How are we able to deploy often and a lot and still keep everything up? So Amazon Corretto is a distribution of OpenJDK. It's a project my team started in 2016. We did it to be able to support all our services. Amazon is a big Java shop. We have a lot of services running on Java, and we found that we cannot rely on a binary distribution. There are too many bugs. There are too many breaking changes at quarterly releases, and that made patching security hard. So we wanted to build Java from source. As I said, we started in 2016. Somewhere in 2017, we had a large chunk of the company running on Corretto. And early 2018, we moved pretty much all the company to run on Corretto. Corretto is a downstream distribution of OpenJDK. The OpenJDK project, 8U or 8 update and 11U, are now maintained by the community. There are multiple teams doing that, but the Corretto team is a big part of that process. And we maintain the OpenJDK of every other downstream distribution from that. So if you're using, let's say, I heard some people here using the Red Hat distribution, you're using backports and security patches my team has been working on, regardless if you use Corretto or not. So thank you for that. We provide at least quarterly releases. That means whenever the security patch or a CPU is released by Oracle, on the same day, Corretto will release a security patch. And the reason I say quarterly at least, it's because every quarter there are security patches coming out, like clockwork. You know, you can look forward for a few years and know exactly when the security patches are coming out. We might actually do more if we find critical bugs or if we find performance improvements that we think you can't wait for 2 or 3 months. But generally, we try to maintain it at a quarterly release to reduce update fatigue. Corretto is a drop-in replacement for hotspot-based JDKs. That means if you used, let's say, another JDK, you can just take it out, drop Corretto instead. The same flags will work. There's no changes to your code. As an example, in 2018, we took about 10,000 Amazon services, and over a period of a few weeks, swapped a few hundred services a day, completely automatically, and we had a single break that had to do with a common library this service was using, and we had to change the class path, and that was it. No regression, no concerns at all with that. Corretto supports Linux, Windows, Mac OS. We have Docker images both on Docker Hub and on ECR, depending where do you want to trust your Docker image to come from. And we support x86, 32-bit, 64-bit, and ARM. So if you're using the A1 instance, Corretto works on that as well. The project is public on GitHub, and you can find more information in the link below. Corretto right now is an LTS release only. That means Corretto 8 will be available until June 2023 at least. If you need more, please talk to us. But that is the current formal commitment that we're making. Corretto 11 has a little over a year additional life over Corretto 8. So where do we use it? We run pretty much everything in Amazon. So if anybody here ever bought a package from Amazon, you've been using Corretto. If you're using AWS, you've been using Corretto. And this year, Corretto 11 became the default Java implementation or default OpenJDK implementation on Amazon Linux 2. And between the time that we wrote this and today, also Elastic Beanstalk introduced support for Corretto 11. I'm going to take a moment to talk about the Amazon Corretto Crypto Provider. That is a module that you can install from Maven Central. You can use it regardless if you're using Corretto. It works on Oracle JDK and Red Hat on pretty much any OpenJDK implementation, 8 or 11. And what you can see here in these graphs is the improvement in CPU consumption. The left graph is the more, I would say, extreme situation where the CPU was spiking almost to 95%. And after using ACCP, you can see it dropped to roughly 10%. A more milder example would be on the right side where you can see roughly 20% reduction in CPU. The nice thing about ACCP is you don't have to change your code. If you ever use Bouncy Castle, it's a similar pattern, except it's a lot more efficient. So give it a try. Again, ACCP has been used in production in Amazon for a long time, and we released it earlier this year as an open source project in the GitHub Corretto repo. Anybody likes to watch TV? So Netflix deployed ACCP, and their statement says that up to 90% of crypto overhead reduction. What does that mean to you? It's great to have less CPU utilization, but it also means that you as customers can take scenarios that previously just you couldn't use crypto. You want to use, for example, if you want to use SSL between your services, and previously it was too expensive, you install ACCP and now it's hardly noticeable, the difference in CPU, and now you're more secure. In the Netflix case, they deployed it to thousands of cloud instances for Cassandra and from Memcached, and they've seen, like we discussed, a 90% reduction. Also, in terms of how easy it was, the process, when I tried with teams and we sit in a conference room and say, hey, here's ACCP, there's more details to what it does, you want to try it out, and it turns out the work is, if you use Maven or Gradle, you add a dependency, you add a property file, and you're done. That's it. So within half an hour, you can have a test instance up and running and see the value for yourself. So I encourage you to go back home and give it a try if you haven't already. Anybody here already using ACCP? Great. One, I think. So really good thing to go home and give it a try. And I'm going to pass it on to Niall, who knows a lot more about Lambda than I do.
Cool. So first of all, who here has heard of Lambda? Cool, great. Hopefully lots of hands there. Who's using Lambda? Great. And who's using Java on Lambda? Okay, good numbers. One thing I want to clear up here, we're talking about how we've used Corretto in the Lambda services themselves. So this benefits you if you're using Lambda, whether you're using Java runtimes or Python or Go or anything else. So that's just one thing we want to call out. But let's take a little bit more of a look at Lambda. And first, a few details to help you understand the scale of what we're talking about here. Firstly, AWS Lambda is a compute service to help you run code without having to provision or maintain servers. It's available in every AWS region, and it processes trillions of customer invokes per month across hundreds of thousands of active customers. AWS customers use Lambda to build highly scalable, highly secure, and highly available services. Let's take a bit more of a look at the architecture of Lambda. So our customer invokes arrive to us through our application load balancer and then into our front-end service. And this is a service we'll focus on here today. The front-end service has several responsibilities, including authentication and authorization of requests, concurrency limit checks for functions, and mapping to a Lambda worker. Once we have a Lambda worker, we then execute the invoke on the worker and return the response back to the customer. So this front-end service is orchestrating effectively the invoke. And one thing that's critical to note here is that any additional time taken in the front-end service adds to the time it takes to run customers' functions. So this is an area we really want to optimize for. We really want to improve our performance here because it's going to directly improve customers' performance. And as we start the story here, this service is running on Corretto 8. So another aspect that we think a lot about in Lambda is how we scale and how we manage the growth that Lambda is constantly going through. We always have the option that we can increase our fleet size, add more front-end hosts, but another option we have is to look at how we can improve the efficiency of each host. And we really love to improve our efficiency because it gives us cost savings that we can then pass on to our customers. But not only that, it actually improves performance for our customers as well. And now how do we decide at any given point whether we're going to increase our fleet or find ways to improve our efficiency? Well, we measure. And there are many metrics that we measure and we dive deep into to understand what the best solution will be at that time. So let's have a look at some of the things that we measure. As I mentioned, latency is a really critical metric for us, but we don't measure the entire time it takes for the request because customers' functions themselves can take up to 15 minutes to run. So if we look at just the response time, it's not a particularly useful metric for us to understand our performance for customers. So what we look at is our overhead, which is the time that we measure that Lambda services have added to the execution time. And this is what we really want to shrink down as much as we can. This graph is showing us our P50 overhead. Unfortunately, I can't share the exact numbers. But one thing that's interesting to note here is when you just look at P50, you're not necessarily getting a lot of useful signal out of it. It's a flat line, it looks good, but 50% of invokes are actually receiving higher overhead than this is. So once we start adding more percentiles to the picture and we see our P99, you can see straight away you have some perspective here, and also there's more variability in the P99. We can then go further and look at P99.9 and even P99.99. And at P99.99, we're talking about one invoke in 10,000. So that might sound like a relatively rare case that's not particularly worth attention, but for us, this really matters because at trillions of invokes per month, we're talking about billions at P99.99. And so the question of which of these percentiles do we care about, the answer to that is all of them. And we care about them for different reasons. Some of our customers are really sensitive to their average performance, and that's what they really care about the most, while other customers are more interested, or also particularly interested in their high percentile latencies. They want to know what their outlier cases will be. And when we talk about scalability, another thing we want to do is try to compress the distance between the high percentiles and the low percentiles, because that gives us more headroom, and it means that we can improve our performance and improve our efficiency. So when we're trying to improve our high percentile latency, one of the I guess, usual suspects you're going to look at is garbage collection performance. And so we started measuring pause times or pause durations for each of our garbage collection events. And what we can see here is our P1 through to P99.99. And it's important to note that these percentiles don't map directly to the latency percentiles because in this case, we're measuring garbage collection events, which happen at a much lower frequency than invokes. But you can see that our P1 is 50 milliseconds for a garbage collection pause, and our 99.9 is 140 milliseconds. So these numbers, at this point, our service is healthy, there's no particular risk here, but we're starting to get a feel for some opportunity that we have to improve this performance. So when we want to look at improving our garbage collection performance, we start looking at our heap usage and our heap occupancy. We want to know how much headroom do we have in our heap after the garbage collector has cleared out all the garbage. So in this graph, we're looking at our P1 through P100, and we can see that the host in the fleet that has the most heap occupancy is running at about 23% heap occupancy. If we saw that much higher, we'd be concerned there wasn't much headroom for the garbage collector, and that would be forcing it to run more frequently, which would then impact performance and impact customers' performance. But this graph tells us we're actually pretty healthy here, which is good for us to know.
So this is an interesting graph that we use on every single service in Amazon for other reasons. So the reason I was talking about has to do with when the numbers here are higher, the garbage collector is going to work harder. But this is also where you have headroom. CPU is not the only measure that determines when your host is going to fail or when you need to scale. However, if you use the standard JMX metric for heap memory, that metric is unreliable. It basically hides if you want to think about it, an iceberg. Especially if you use the G1 collector, the collector is trying very hard not to collect until the last minute. So your heap memory may show 90% utilization, where in reality, you're using 5% of the memory and the rest is just garbage. How do you know if your service is going to be in trouble or not? We thought quite hard on this problem, and we came up with this new metric called heap memory after GC. And what we're doing is we're collecting data after a mixed collection has run, and we do that across all types of collectors. And then now we have a standard graph, and we typically use P100 as an alarm. And if one of your hosts is starting to use over 75 or 90% memory, we will alarm. And with that, we're able to catch outages. Maybe sometimes it's a day, sometimes it's a month before it's going to happen. Otherwise, teams just get desensitized and don't see that data. This metric is not available in the JDK, but we just introduced a sample that will help you basically write the same metric for your system. If you go to GitHub, and unfortunately I don't have the link here, but if you go to GitHub Corretto 8, there's a pull request number 177, and that pull request has the sample that will show you how to connect all the numbers and do the metric math that will produce this graph. And so while this is a good metric, another thing we recommend to do is to capture GC logs on a regular basis. How many people here are capturing GC logs? Nice, about 15, 20%. This is another homework for you to do. I would suggest when you go back home, or if you're developing in the cloud, you can do it now. Add these flags to your Java process. You want to print the GC details. That gives you enough details. You want to put files, you want to name the file. You want to rotate the files. That means if your application has crashed, you have one safe file to look at. So these are the parameters we use by default in Amazon. We use 4 files, and we limit the file size to 10 megabytes. There's more flags and more to learn here, but this is a very good start. So what do we do with this in Lambda? When we look at these results, what you can see is at 518.32, we cleaned up 11.7 gigabytes. The collector went through and collected about that much garbage, and about 5 seconds later, he did it again. If you notice, there's another 0.1 gigabyte that wasn't. But roughly speaking, 1.7 gigabyte collected. And if you do the math, you can see that we are allocating at about 2.1 gigabyte per second. That's an interesting metric. It varies with load, and it varies with the type of request you're seeing. But when the numbers go above this 1 gigabyte mythical number, you want to start looking at it. This is not a scary number, but it's a number, it's a meaningful, significant number that encourages us to look further and dive deeper.
Cool, so yeah, as Ishai said, at 2 gigabytes a second, everything's healthy, but we start getting a feel that there's some opportunities here. And it's important to note that that's a really useful metric, but there's not much nuance to it. We're not seeing the variability through the day or at peak times or across the fleet. So we want to get a deeper understanding of where our allocations are coming from. And this is where we started to look at how we can measure our allocation rate at a per request level. And this is a really valuable metric to us because it gives us a cost per unit of work. and that's independent of how we scale. If our traffic grows, this metric should stay consistent. And in fact, if we start seeing this trending upwards, then that's a reason for concern, because that's starts looking like a regression. And that would be something we'd immediately be investigating, because we want to keep that number steady. In fact, we actually want to improve it. And this number also provides a really great way to measure the impact of your improvements, because it will show you at a per unit of work how much you've made a difference, which will be independent of how much traffic is happening at different times you're comparing your data. So how do we go about measuring at a per request level? Well, here's some sample code of how we do this. We're using this thread MX bean that allows you to ask for how much memory a given thread has allocated at a specific point in time. So we can measure this at the start of a request and at the end, and we now have a picture of how much memory we've allocated to run that request. And this works really well when you have a threading model that is one thread per request. As we all know, you can get more performance or more scalability through using continuations and asynchronous processing. So if you have a model like that you can modify this, you need to get into your thread scheduler and help it follow the thread as it's moving, as the request is moving between threads. But it is doable. And this gives us, as I mentioned, a much clearer picture.
So while this is a great metric, if you use it today with JDK8, what you'll find is this is quite expensive. So particularly for an application that uses a lot of threads, let's say you use 1,000 threads in the application, every time you call the get thread allocated bytes, it allocates an array with enough cells to cover all the threads. So you're seeing quite a big allocation just to do a measurement, right? So it's like quantum physics. The observer changes the process. We don't like that. So with the Lambda team, what we did is we reduced it to a sampling, and it will sample a few % of all the requests. We don't like that. So there's a pull request out there that is improving that to a point that you no longer have to worry about it. You can run it 100%. So when that pull request makes it into Corretto, we're deploying it right now in Amazon. I think I discussed with a few people earlier how we do our testing. We test in production with Amazon services, with AWS, before we release it to the world. Especially changes like that are very deep into the guts of Java. We want to make sure that we're not introducing regressions. So right now, this is in testing, in production, but the plan is very soon to put it into Corretto and then contribute it up to OpenJDK. And when it's done, you can run this metric 100% of the time, or at least higher percentile.
So let's have a closer look at the kind of data we get out of this and why it's so valuable to us. So here we're seeing our P1 through P99 percentiles of allocation per request. And at P1, we're about 500 kilobytes per request, and at P99, we're about 3 megabytes. And one thing this is reflecting is that actually there's a range of amount of work required of the service to service invokes depending on the actual request itself. So that's one reason for the variation here. But again, these numbers are not particularly concerning, but we really are starting to get a feel for the opportunity that we've got here and how we can start improving these. And so another way this is valuable is that we can correlate improvements here against other metrics to start seeing, help us explain what's going on with the improvements over time. So now we've got a whole lot of opportunities in front of us, and we need to find some ways forward. And I'm going to pass over to Yishai here to talk more about where JDK fits in this.
So the obvious next step here was to look at JDK 11. But as I heard from many people, it's kind of daunting moving a major version of Java. And a lot of teams in Amazon and outside were kind of holding back. One of the reasons is JDK 9 came out in 2017. Introduced a lot of really cool features. In fact, most of the cool features in JDK 11 were already introduced in JDK 9. However, JDK 9 was missing one crucial feature, and that is it did not have long-term support. So we've seen teams move to JDK 9 only to learn that only a few months later they had to abandon it because it wouldn't get security patches or any patches. Moved to JDK 10 just to find out the same thing and got that update fatigue. So JDK 11, I would say number one feature is long-term support. It was introduced in 2018, and I want to jump quickly to this chart. How many of you have seen this chart or familiar with it? Okay, not enough. This is a very important chart. So on the bottom, you can see the lifetime of JDK 8 or Java 8. Java 8 was supported for a long time, but early in 2019, you can no longer get free updates, or at least from the Oracle JDK. And then OpenJDK, or the company supporting it, announced that we will support it until 2023. And that's the same data applies for Corretto, except as our customers, if you need more at the end, please talk to us and we'll figure out what to do. My guess, it's going to be hard to get off Java 8. Java 11, same pattern, introduced in 2018 and going to have support all the way to 2024. But all these other versions, 9, 10, 12, 13, 14, they're released, they get roughly a month after they get released, they get a security patch. They get another one 3 months later. And then what happens is they don't get security patches anymore, but the next JDK, so if you're on JDK 14, JDK 15 will get introduced, first without any security patches. You have about 4 weeks to move your application from JDK 14 to JDK 15, and then JDK 15 drops a security patch. On that timeline, Java 8 will get the patches, Java 11 will get the patches, and Java 15 will get the patches. And if you're in JDK 14 at that point and you're, it's like musical chairs. You stand there on your own and you're not secure and nobody will give you a security patch. So for that reason, what we're seeing customers do, most customers do, is pick a long-term supported version because they have the guarantee that they know they can move. You don't have that guarantee with feature release. Your third-party dependency might not support you. If you can do everything from source and you're deep in the stack, of course you can do the job yourself. But what we see most customers are just unable to do it. When we experiment with customers with feature releases, we've seen about 1 out of 10 customers able actually to keep up in that move with the security patches, and most customers just roll back at the time to JDK 8. But JDK 11 has been out for over a year now. We've been starting to run it in production. Initially, like with every new major version, there are many issues, but there's been about 5 patches, I believe now, and it's quite stable. So what's new in JDK 11? A lot of cool features. It's the first time modularization comes in. Flight Recorder is now open source. There's low overhead heap profiling and new HTTP client, and you can use var. I'm not going to go into that fight, but if you want to, you can use it. But that's actually not what I want to talk about today. I want to talk about the free stuff you get without touching your code. And that is the G1 garbage collector is now a default collector. We think it's a great collector for most cases. Unless if you're doing a batch operation, stay with parallel. Other than that, if you care about latency and you don't want to tune your app, G1 is great. It parallelized the full GC, so if you hit full GC, it's a lot faster now. Improved the object copy phase, again, means the mix collection worked better and faster, and just generally a lot of bug fixes that went in there. It also introduced compact strings. How many people here know about compact strings? 1, 2, 3. Okay, here's another good one. So compact strings were first available in JDK 9. What they do is, instead of using 2 bytes per character, in this case, let's look at the word Amazon. You have 0A, 0M, 0A, and so on. Very, I would say not efficient is a nice word. We all know about UTF-8, but you had to go and explicitly use UTF-8, which was really hard to do. You don't own the whole stack. You can just do it on your own. What Java 11 introduced is this new thing, which called compact string. That means if Java recognizes that your string is purely ASCII or the Latin 1 code page, it will compress your string in half. It will add a byte called decoder that will tell it it's Latin 1. And other than that, you have half the string. It's beautiful. You don't have to do any work to get it. And it turns out that many applications use string heavily, right? You allocate basically objects, arrays, and strings. And for most applications, what we're seeing is they don't actually localize the data. A lot of the data you allocate is just machine strings you move around, or log entries, or things like that. And a lot less of your, generally looking at most of the applications that we've seen, a lot less of the strings are, internationalized strings. So there's a good chance you can reduce your heap size, the part of it that uses string, by 50%. And all you have to do is upgrade. I want to take a sidestep to kind of convince you that this is something worth looking at. So anybody familiar with duplicate strings? Again, a few people. OK, this is a nice thing to try. Take your Java application and turn this flag on, -XX plus use string deduplication. The min bar for that is you got to use JDK 8, U20, which I really hope you're not using anymore and using something a lot newer. And you have to use the G1 collector. Even if your application doesn't use the G1 collector, turn it on, give it a try. What happened for Lambda, they turned it on, and they've seen 80% reduction in their string allocation. Pretty amazing. It turned out that a lot of libraries allocated the same string again and again and again and again. We've seen some of them replicated tens of thousands of times. But when you use that, the JDK or the JVM is trying to synchronize your access to the string. It wants to say, I've seen the string before, hold on, let me give you a reference to the string. And what that does, it actually creates a bottleneck that increases the GC pause time and increases your latency. So not a great idea unless you're running on a server, you're memory bound, you can't change it, you don't worry that much about latency, you just want to keep running, it's a great flag. But other than that, not so good. However, if you turn it on, you can measure your memory. You remember how to measure memory from before, right? You can see if it's valuable to go to JDK 11 without spending any time on coding, changing dependencies, or anything like that. So give it a try. With the Lambda team, it really encouraged them to move to JDK 11. Another thing you can do, even if you don't want to move to JDK 11, if you run with these flags and you've seen a significant reduction, capture a heap dump. You can use a tool like the Eclipse Memory Analyzer. In that tool, you can find the duplicates. And you can, typically, if you see the string, it's very, I won't say very easy, but in the cases I've seen, it was easy. You can figure out which library created that string. And many times, you can just go back to that library. Maybe you own it, maybe it's your code, maybe it's somebody else's code, maybe it's open source. But you can go back to that project and say, hey, you're generating hundreds or thousands or tens of thousands of unnecessary memory allocations. Can you please take it out? If it's open source, go give them a pull request, right? And everybody wins. So we've done some of that with Lambda, but it was still not enough. So I'm going to pass it back to Niall, who's going to talk about what they actually did to move to JDK 11 once all this convinced them to go.
So yeah, the good news is that getting the service up and running took us around a day. We had some dependency changes that we had to make. JAX-B, we have a transitive dependency on. It's not bundled in JDK 11 anymore, so we had to go and find that dependency and add it back in. Log4j you do need to keep up to date with, but it turned out we were already there. With Mockito and ByteBuddy is where we ran into a few more issues, and I'll talk about those more in a moment. But if you're not familiar with them, Mockito and ByteBuddy we use for our mocking framework for our unit tests. Lombok we use for some code generation in a pretty light way, and you do need to get that updated as well. But basically, in about a day, we had all the dependencies fixed, and the service was up and running. And this is really encouraging to say that, OK, maybe this isn't going to be quite as difficult as we thought it was, but it's just the first step. And then we ran into this slightly less easy part. As I mentioned, we had a pretty major upgrade on Mockito. We went from 1.10 to 2.25, and it turns out that there were a few breaking changes introduced in Mockito in this time, and there's quite a wide range of versions that we've upgraded here. And we also had some compatibility issues with ByteBuddy that were fixed just by upgrading. So at this point, we now had some failing tests. In fact, we had a lot of failing tests all through our code base. And this became an exercise in working out what was going wrong there. So we always keep up to date with our security patches, but one thing we really learned here is that if we'd kept up to date with our major versions of even our basic test dependencies, we would have had an easier time here. We have a really test-heavy code base, and so migrating earlier would have meant we would have written more tests in the newer code base, and it means that every update you're doing is a smaller change, so you're not dealing with multiple breaking changes at the same time. So that was a lesson learned here. And I'll go through a bit more of the details of some of the issues that we hit. So the first one we found with Mockito was the argument matcher for any string, any integer, etc., was no longer accepting nulls as a valid value. And it turned out we were using this pattern through our code base in a lot of unit tests. So the fix is easy. You just change it for a nullable matcher and away you go. The problem is that when you have to do this many times through the code base, every time you find it, you need to investigate and understand, is the test broken just because of the argument matcher, or is there something else broken here that I need to make sure is actually fixed? So this sort of multiplies out into a bit more of a laborious piece of work to fix every single point and make sure that you're not just papering over problems that are being introduced in the upgrade. But we didn't find any issues. Everything was fixed by moving over to the nullable matcher. Similarly, Mockito has a change where if an interface throws a checked exception, but the implementation doesn't, then Mockito will no longer allow you to set up a mock of that implementation to throw the exception because it's not valid anymore. And this also highlighted for us some cases where we had some tests that were testing scenarios that actually couldn't happen. And so that was really valuable because we got to delete some code. But there were also other tests we had where instead of mocking the implementation, we really needed to be mocking the interface. And again, this was an easy fix, but multiplied out over many places became a little bit more of a workload there. But we got it done. So at this point, we have a working service, we have working unit tests, and we need to start thinking about how are we actually going to roll this out. AWS is in 22 regions worldwide, and Lambda's in all of those regions. So when we do rollouts like this, we think really carefully about how we can make sure we're not introducing risk for our customers. Normally, we have once we get through all our test stages, everything's green, we go through a completely automated deployment where we run integration tests and everything, and it's hands-off deployment with lots of monitoring and alarms through the way and rollbacks. But in this case, we wanted to take a little bit more time to make sure that what we were doing was safe for our customers. So we ran a pilot deployment in a couple of regions before we started our process. And this let us build some confidence that the deployment was going to be successful. So what were we really trying to prove out here? We were looking for any unexpected surprises, particularly any issues that might turn up, say, a week or two after deployment. We don't want to get through a worldwide deployment and find out that now there's a worldwide problem. So this pilot process really helped us get confidence in that we weren't introducing issues by moving to JDK 11. And this really goes to our constant approach that we have in AWS of limiting our blast radius. We want to make sure we're not exposing our customers to risk while we're making these kinds of changes. So with these large-scale changes, we do move more slowly. We take more time to think about how it's safe to roll them out and build that confidence first. And this is an approach that obviously you can use as well. So our automated pipeline goes through regular build and unit test sections, and then several stages of integration testing, load testing, etc. And this is all before we get anywhere near production. But once we start moving to our first production region, which, by the way, we choose our production region, our starting region carefully, because we want to make sure, again, that we're limiting blast radius. We're not choosing a really large region, but we need to make sure that we're getting valuable information out of this and it's giving us confidence to move forward. So within each region, we have several sub-stages, staging, canary, and production. And all of these stages are using the same Lambda backend, but staging receives the deployment first, and it's only working on test data. It doesn't touch any production customer data whatsoever. And so this is the difference between staging and our previous test stages is this is actually testing the new release in this production region with the production backend running. So this is giving us real confidence that this new version of the front-end service is actually safe to deploy in this region as opposed to safe to deploy in test regions. And the other thing we can do with staging is actually run test traffic through our staging environment and also through production to be able to compare and make sure that the two versions, the old and the new version of the software, are compatible. that they're not going to do anything that might, say, corrupt data in the database or cause poison pills between the new and the old version. And again, it's really important to stress that this is all running on test traffic and test customers. So this is not putting any production customer traffic at risk at all. But once we gain confidence here, we know we can start rolling this out to production. So we move forward next to our canary, where we run a small fraction of our fleet on production traffic with the new version. And this runs with monitoring and alarms, and we build more confidence at this stage to make sure that everything's looking good before we then progress forward to the full production rollout. And the production rollout itself is gradual. It moves through the fleet gradually, and again, there's alarms and metrics and rollbacks. So the point here is that at each stage, we're progressively increasing our confidence that the deployment is safe. If you want to take a similar approach, you can use AWS Code Pipeline to do this, which will let you build a staging, test, and production stages and regional rollouts, and let you do gradual deployments through fractional deployments as well. So this is an approach you can take home and you use in your own services as well and customize to fit your use case. So at this point, we've got a successful pilot, we've got a successful rollout, so we're pretty much done, right? Well, no, we've gone through the first two phases here. This is an iterative process we go through all the time at Amazon. We've measured our system to understand where we have opportunities, we make improvements, and now is actually the most important phase where we need to observe the results, because this is often where we learn the most out of the whole process. And because often the results can be more than we expected or less, and often it helps us identify new opportunities to start again with. So looking at our requests our allocation per request rate, on the left here is Corretto 8, and on the right is us running under Corretto 11. And we're seeing a really nice improvement here, around 15 to 25% across the percentile range. And this is mostly compact strings at work here. It's really exciting for us. We'd love to see a big improvement at P99, but it's really exciting to see improvements at P1 as well, because that's where we're knowing we're infecting every single invoke running through the service. So how did that improve our GC pause times? It turned out quite a lot. Again, we're looking here at P1 GC all the way to P99.9, and we're seeing 30 to 50% improvement in our pause times just from moving to JDK 11. This is a really exciting win for us, and again, it's really valuable to us that this is happening not just at the highest percentiles, but at the lowest percentiles as well. And the reason why we had so much of an impact here was two things combined. It was the allocation improvements with compact strings combining with the G1 GC performance improvements. So you've got a garbage collector that's already faster and we're giving it less work. So they compound together and we get a really nice win out of this. And then the ultimate aim for all of this was to improve our latency. So again, we look at this across different percentiles. And at P99, we're seeing a 20% improvement in our latency. If we move down to P99.9, we're actually getting 40% improvement on our overhead. And that's really valuable to us. So we move forward to P99.99, and it actually turns out the gain is a little bit less than at P99.9, which was counterintuitive to us. We were expecting, as we moved into the higher percentiles, that improving garbage collection performance would have a progressively larger impact for us. And we're still very happy with 33%, but what this tells us is that there are also other factors at P99.99 that are impacting performance. And so this helps us know that we need to look at other places, and we've identified several new opportunities in this area as well to move on to. And that kind of goes back to that iterative improvement process. So at the end of all this, how many bugs did we hit? How much customer impact was there? I'm super glad to say there was none. And hopefully all our Lambda customers are glad to hear that as well. The pilot process really helped us build confidence to know that we could move forward without putting our customers at risk. And we didn't find any surprises at all during the pilot. This was rolled out worldwide in August, and since then, AWS Lambda customers have been enjoying faster invokes since that point, so that's good news for everyone. But it also, as I mentioned, it's helped us identify a whole lot of new opportunities. So we learned a lot from the process, and we get a lot of new opportunities to improve latency further through this. So I'm going to hand back to Yishai to close out here.
Cool. So one more thing I want to add. So there's a lot of concern with teams about jumping these major versions. And what we found is really useful is to do what we just did here, if you move one of your services to JDK 11 or to anything else interesting, go back to your other teams in your company and tell the story. Because what we've seen from this, the work we did with Lambda, we've seen many other teams get excited by it, pick it up, and go do the same thing. And then they come back, and you create that flywheel of excitement around doing these improvements. They're no longer scary. Your management is going to be like, why are you not on JDK 11? Look at what these guys have done. So tell the story. Talk about your successes. It really helps other teams move along. But if I want to recap, JDK 11 is here, and it's been here for quite some time. It's ready for prime time. Pick it up. Go try it out. I wouldn't say it's 100% perfect, but JDK 8 ain't either. The other thing, I don't want to say we learned it from this process, but it really reinforced it. Update your dependencies often. Don't wait for these big jumps. It becomes a lot harder to update. Remember, there's teams like my team that work on the JDK. There's a lot of teams that work on all this open source software that you're using, whether you know it or like it or not. They keep improving the software. Just you get free bumps in your performance, lower cost, all these things just by updating. Do it. You'll save yourself time and money, and you won't have to. You'll find in many cases that you don't have to build code and improvements to get that kind of result. At the same time, I really recommend using CI/CD. When you start making these massive changes, imagine you have 100 or 200 dependencies, and you keep updating them all the time, you can be lost without a CI/CD system. So invest in your CI/CD. It will really help you build confidence in making faster and efficient deployment, also safe deployments. However, if you hit a large change like this, even if you have a CI/CD, it is okay to say, let's pause, let's think about it, let's figure out where the risks are, be a little more old school, and think about how you get this stuff out. Just want to kind of wrap it up with a shout out to the Corretto team. We're powering Amazon, we're powering AWS, and we want you to try it out. So give it a try, let us know what you think. And one more thing. So on November 18th, Lambda announced support for JDK 11 using Corretto. So if you're waiting to use Java 11, and your reason for not upgrading was Lambda doesn't support it yet, excuse is gone. And if you're running Java 11 on Lambda, you are going to use Corretto. That's the default runtime over there. You can use the console to set up a Java function, or you can use the CLI to do it. Well, thank you very much. And please complete the survey in the mobile app. And if you have any questions, we will be out the front. Feel free to stop and bug either of us.